Good morning, everyone, and a very warm welcome to today's edition of 45 Minutes On, hosted by the Aluminium Stewardship Initiative. I'm Gabriel Carmona Aparicio, Circularity Research Manager here at ASI, and I'll be your moderator for this session. So today's topic is both timely and technically important, so we'll be exploring how aluminium and other materials used in buildings can be designed for multiple life cycles, not just reuse or recycle at the end of life, but truly retain in high-value applications through intentional forward-thinking design. So we are very pleased to be joined by Dr. Rebecca Hartwell, who will be introducing the concept of reclamation potential assessment. This is a new design tool that helps quantify how components, selection, and design decisions influence resource efficiency across multiple building life cycles. So a bit about Rebecca. So she is a postdoctoral researcher at TU Delft in the Structures and Material Group within the Faculty of Architecture. So Rebecca holds a Master's of Engineering in Material Science and Engineering from the University of Manchester and a PhD from the University of Cambridge, where she focused on material efficiency in architectural glass and facade design. Her current work at TU Delft bridges research and practice, so developing tools and methods to evaluate the reclamation potential of building components and advancing reversible construction techniques to enable safe demountable assemblies. She works closely with industry partners, including Perma-Stilisa and Autodesk, and remains committed to scaling research into practical real-world applications. Before I hand over to Rebecca, a quick note on how we'll be handling questions today. So next slide, please. So you can type your questions into the Q&A window at any time during the session. Just click the Q&A button at the bottom of your Zoom screen. If you prefer to ask anonymously, you can check the Send Anonymously options. We will try to cover as many questions as we can during the last minutes of the sessions, either live or even via written responses. If you encounter any technical issues, feel free to flag those in the Q&A as well. Someone from the ASI team will try to assist you. So with that, I will hand over to Dr. Hartwell. So Rebecca, the floor is yours.
Thank you very much, Gabriel. It's a pleasure to be with you today, and I hope we can have a lively discussion towards the end. So the topic I'd like to present to you today is on looking at assessing the reuse potential of multi-component systems. And in the context of aluminium, which typically accounts for around 24% of global use within construction, it's really quite pertinent to understand how we can reuse these elements that are embedded in existing stock. So 97% of the European building stock is considered as operationally inefficient today. And by operationally inefficient, I mean looking at the energy required to heat, cool, and light a building. So there's a huge need to try and understand how we can renovate existing buildings in an efficient way so that they can perform better during their life cycle. And the facades and the internal mechanical and electrical surface are a key contributor to the operational performance. And typically within those elements, facades and mechanical and electrical surfaces, we do use high volumes of aluminium elements. So looking at how we can design those in an effective, efficient way from a material point of view, but also for reuse is key. And so as I mentioned, there's renovation as a challenge to tackle, but also how we can develop new designs and systems that promote future reuse and high value recycling. So the circular material use rate in Europe is around 12%. And this is typically looking at low-grade recycling or other recycling options. For aluminium, of course, that's much higher within the construction sector, around 90 to 95%. But again, this circular material use rate is mainly focused on recycling, which may be closed loop, but not reuse of aluminium elements, which could be potentially a more environmentally valuable route to deploy. And so if we look at this in terms of environmental impact and embodied carbon, so carbon dioxide equivalent, if we look at the building as a series of different elements, and I mentioned aluminium mainly focuses within the facade and mechanical and electrical services, you can see from an upfront embodied carbon perspective, these are relatively high contributors to the total building's upfront embodied carbon. So understanding how we can recover these elements effectively is really key. And what's really quite important when studying aluminium in existing building stock is how components are connected to one another. So in the past, where we may have used construction techniques that were more simple, for example, this dry stack stone wall, which you see on the slide here, as you can imagine, with these kind of construction methods and these kind of mono-material assemblies, whilst requiring fairly high level of craftsmanship to produce, if we were to think about reuse or reconfiguration, it's not so difficult to imagine in this case. But then if we start to look at the elements that we're now incorporating into our existing building stock to try and improve functional performance and operational use, we start to rapidly build up much more complex layers. So for example, we can see on the slide here, looking at aluminium composite panel, we may start off with an aluminium backing sheet and then start to incorporate different insulating cores, polymeric insulating cores, which are bonded by an adhesive component, and then bonding that core to another backing sheet on the other side, and then coating or finishing the aluminium sheet. So quite quickly, you start to see that we're building up these kind of complex building elements without much consideration for what will happen at end of life. There's an interesting concept put about by William McDonough and Michael Braungart in their book Cradle to Cradle of the concept of the monstrous hybrid, which is a product that contains a mixture of materials or assemblies of components from which it is not economically feasible to recycle or salvage the raw materials after their current life. And so, unfortunately, this is quite telling for many of the building elements that we're starting to incorporate in our building stock, or have been for the last few decades. And so my research really focuses on how can we continue to make technological advancements that will improve the building performance in operation without foregoing this reclamation potential, which I'll define throughout the course of the webinar today. But essentially, it's the ability to easily reuse and recycle elements from our building stock. And as I mentioned, just to highlight, it's not just the composite panels, but there are many other applications of aluminium within buildings, for example, within sun shading louvers, which are quite commonly used now in more high-end facade systems. Also as spacer bars within insulated glazing units, where you can start to see this kind of monstrous hybrid assembly building up once again. And also very frequently as framework elements for curtain walling units for buildings, which enable you to have a very lightweight hung facade system that you attach to the primary load-bearing structure. And these aluminium elements can be quite bespoke, but also express a level of standardization. So looking at opportunities for reuse is really key here, but that really depends a lot on how these connection types come together. So when looking at minimizing environmental impact as a whole, there are two key themes to focus on. The first is thinking about how can we potentially reduce material upfront and use less material by design. And the second is looking at the recovery stage. So how can we collect existing materials in our building stock in a way that's efficient, that enables us to reuse and potentially remanufacture products at high value. But what's often missing is this link between design choices in terms of material selection, how components are connected to one another, and their eventual form, the level of standardization, to the recovery. So how does the choice of material or how a component is connected to one another influence the ability to reuse that product? And I think this is a really key gap that's been expressed by industry. So we've conducted many different interviews and surveys with industry, primarily with the facade value chain, so the building envelope value chain. speaking with clients and developers through to manufacturers and demolition contractors. And at present, whilst there's been many recent developments in this area, at present, facades, a building envelope, is often seen as a highly complex component for which dismantling is typically overcomplex and not worthwhile. And you also have a very wide mix of service lifetimes within the facade itself. So not just the building as a whole, but also within the facade, the different components that you have within the facade. So this can influence the obsolescence of the total component. And some of the key enablers for reuse that have emerged from these qualitative studies actually arise around the likes of quantifying the environmental value of design for disassembly, improving logistics for different take-back schemes to enable greater percentages of reuse, and also quantifying and justifying the economic viability. But today I'd like to focus on the quantification of the environmental value. So there are some existing methods, of course, for evaluating life cycle assessment, using life cycle assessment as a way to evaluate environmental impact. And you can use this method to assess many different environmental indicators, for example, global warming potential, or the use of renewable or non-renewable energy. And within this method, this internationally standardized method, you look at the life cycle of a building component, product, or building as a whole within these 4 different life cycle stages: A, B, C, and D. Life cycle stage A is related to the production of a product, the primary raw material supply, and eventually the fabrication and construction within a site on a building. And then there's stage B, which is the use stage, so everything associated with the use of the product in a specific application, and also operational energy and water associated with its use. So this includes also within this stage the impacts of replacing components over the lifetime to be able to maintain the product in use, and also any kind of repair procedures that might have to take place. And the life cycle stage C is associated with end-of-life processing. So this is deconstructing a building and its parts, potentially maybe demolishing it and not separating the waste, and any reprocessing costs associated with recycling materials. And then finally, module D is often used to evaluate the benefits beyond the first life cycle, which could be evaluated in different scenarios. And at the moment, that's evaluated as a negative quantity, because essentially it could be a benefit from redeploying these existing materials in a new system in future. And under existing guidance, this is advised to be communicated separately as opposed to aggregated across the full life cycle to avoid double counting benefit to recycling. There are some limitations to this module D as a way to evaluate the circular economy within building products and products as a whole. It tends to focus on single components or material types, so looking at just one material in isolation, as opposed to it being embedded in a multi-component system. And in that sense, it disregards the influence of different connection methods and construction technologies, so the dependencies between how components are connected to one another. There's also some lack of harmonization between different countries in terms of whether or not to include module D. So for example, in the Netherlands, module D is actually commonly included in the assessment method, which can make it difficult to compare products from different regions. And there's also no consideration for future decarbonisation of industrial processes, such as decarbonisation of the grid or localised manufacturing facilities. And to some extent, it fails to account for the uncertainty of the actual end-of-life route that's deployed in practice. So this brings me on to the development of this reclamation potential method, which we've developed as part of my PhD and then more recently within my postdoc here at TU Delft. And the goal of this method is to be able to look at multi-component systems over multiple life cycles and understand how design changes influence the ability to reuse elements over multiple life cycles. So at the moment, we're looking mainly on the building element scale, and we've trialled this process in the context of facade systems, but there could be scope to scale it up to the building level as well. So looking at many different components such as structural floor systems, roofing systems, and otherwise. And as I mentioned, the key part of this assessment is understanding its value in the second, third, or nth life cycle. And why we find facades a particularly interesting case study to look at is that they are often these kind of multi-component systems with a relatively medium-term service life, depending on which industry we're talking about. But from our surveys and interviews, we found that facades typically have a service life of 10 to 50 years. And this obsolescence arises for different reasons in terms of service life, not just technical reasons. But if we were to look at the technical reasons for short service lifetime, it varies very much within those components in a facade system. So for example, some of the motorized components in a facade system may have a service life of 15 years. But some of the framework elements, such as aluminium framework elements, stainless steel cladding elements, and monolithic glass, can have a lifetime of much longer, up to 60 years and above. So understanding the influence of these service life dependencies we found is really key to incorporate in the assessment for reuse potential. So the current project that we are working on is called Project Reclaimed, in partnership with the TKI, which is Dutch government funding agency, and Schouderbouw, who are a facade contractor and manufacturer that are based in the Netherlands and more widely known as Perma-Slese Group globally. And they are responsible for primarily curtain walling systems. And together with the team at TU Delft, consisting of Professor Mauro Overend, myself, Lisa Marie Muller, and Dr. Michaela Turin, we're working at scaling this assessment method up and developing a digital tool to be able to use and interact with, to be able to understand the reuse potential of different building elements over their lifetime. So I'd just like to introduce to you the workflow of the current assessment method. So in this method, we try to first understand the materials that exist in a specific building element as a mix of components, and understand the service lifetime of these materials, so when they are likely to fail over their lifetime. And we assign a probability distribution to understand the performance deterioration of these components over time. So those inventories are standalone inventories that we incorporate into the assessment, but then we have our system-specific data for the current product under analysis. So for example, if it was an aluminium composite panel, we assemble a components inventory, which could consist of the aluminium, the core, the adhesive elements, and also how those components are connected to one another. And then we also have an inventory that details the necessary information for the system as a whole, so fabrication conditions and otherwise. Within this project, we are also looking to develop an automated method to be able to extract this information from construction drawings, so from digital design drawings, AutoCAD or otherwise, and using this to extract all the data related to the components and the connections between components. Then within the calculation process, I'll discuss a little more in detail as I go through these slides, but we assess the product and study as a system network, a map of components and those connections between components. And we also understand the likelihood of these components being replaced over time as a function of their service life. And further in this work, we are also developing a series of disassembly tasks and sequences to go beyond just reversible or non-reversible connection types, to be able to assess the time it takes to assemble a component and how that influences the reuse potential. And the primary outputs of this assessment are being able to understand the life cycle embodied impact over time. So this could be in terms of embodied carbon or other environmental indicators, and also the reclamation potential in different recovery scenarios. And as I mentioned, we're developing this into a simple user interface at the moment, and also some early discussions on it's being incorporated as a software plugin. So just to walk you through some of these key inputs for the reclamation potential method. I'll start, it's one of the key ones is the materials inventory, which at the moment we actually assemble manually from existing environmental product declarations, where we detail the type of material, the different processing conditions, and the associated environmental impact. We could look at automating this data extraction process from EPDs to our materials inventory. But in the next couple of years, we see this information will be more readily stored in a digital format online. So that's how we see this evolving in future. And then we also assemble this components inventory, which I mentioned we're looking to automate at the moment. So this is a digital file showing a construction drawing where we've been able to extract the information from this construction drawing to understand exactly which parts exist and what material those parts are made of, and their volumes, their geometry, to be able to evaluate their environmental impact. And then the other assessment input is the connections between these components that exist. So as I mentioned, this is a key difference as well between assessing Module D. We include this nuance associated with service life dependencies between components. So for example, if we were to have a system, such as that shown on the slide here, with a three-component system, where we had component B and C, which are irreversibly connected to one another, but component A and B, which are reversibly connected to one another. Because component B is irreversibly connected to component C, even though component C has a service lifetime of 10 years and B is 30 years, we have to replace both of these components when component C reaches end of life. So there's an additional environmental impact in this case to be considered. So this is where we really try and account for varying durability of elements within a product to be able to assess true environmental value over time. We assess 4 different recovery scenarios within this method. The first is looking at selectively dismantling the facade element or other building product element and directly reusing it elsewhere. The second is disassembling this multi-component system and reassembling it, remanufacturing it into a new system to be incorporated onto a new building. The third is actually separating material groupings, which is very much widely done at the moment with aluminium products. So separating different materials on site and then recycling it back into new products of the same type. And finally, the worst case scenario as a benchmark comparison, which should be mixing all materials up on site and it going to either low grade recycling options or at worst case landfill. So through this assessment method, just to give you an example, for example, this is a double skin facade that you see on this slide here. And you can start to see the different components, the aluminium-containing components, particularly the framework elements and the spandrel sections, the backing and front sheet for the spandrel sections, also the blind system. And from this construction drawing, we can generate a system network map. And this network map is a series of components that exist in the system and the type of connection between those components. So essentially a node on this map here corresponds to a component in the system that you see on the left. And then these edges between the nodes correspond to the type of connection that exists between these components. So you can think of this as the key data resource that we use to then evaluate the lifecycle environmental impact and also the reclamation potential, where we assess the difference in terms of the deconstruction of different subsystems and reuse potential in different life cycles. So from this assessment, we can evaluate the upfront embodied impact, which may be in terms of carbon or otherwise. So in case of this system that I just showed you here, the double skin facade system, you can see the upfront initial embodied impact, which is 180 kilograms of CO2 per meter squared of facade surface area. And we can separate this out into different components. You can see in this case here, aluminium accounts for around 32% anodized aluminium extrusions, and then the sheet and regular aluminium extrusions account for additional 14% of the total. So already here we can start to see which materials maybe we would like to target for optimizing the material efficiency to reduce the upfront embodied carbon. And I mentioned it's not just the upfront embodied carbon we assess, but also the life cycle embodied carbon over time. So when we have to replace a component because it's reached the end of its service life, we can then understand, okay, at 30 or 50 years, because of that component replacement, we have a jump in the life cycle embodied impact. So we see a growing embodied impact in terms of an environmental indicator over time. And those recurring embodied impacts, as I say, account for those different service life dependencies between elements as well. And then on this reclamation potential graph, so on the left axis, we have the life cycle embodied impact, and on the right, we have the reclamation potential, which is a function of the recovery route that's deployed. And so for the different recovery scenarios, I mentioned the four, I'll show three today: recycling, component, and system reuse. We consider performance reduction factor. And so this performance reduction factor accounts for what materials were used in the first instance and what deterioration might have taken place. So for example, in the recycling scenario, we can't assume that materials go back to the same product. So we map the material in its primary application to the material in its secondary application, which in some instances may be a form of closed loop recycling. But in other instances, for example, here with laminated glass, it may be downcycling to aggregates or even energy recovery through incineration for polymers. So we include that performance reduction factor for the recycling scenario. And similarly, for the reuse scenarios, component reuse and system reuse, over time, we include another performance reduction factor, which accounts for the deterioration of the performance of this component in question. So for example, I've plotted this probability of survival graph here, which you can see for a 10-year service lifetime component. So over time, you can see how the probability of survival of the component drops off very rapidly after the 10-year service lifetime. At 15 years, the likelihood of survival 72% and drops rapidly to less than 5% at 25 years. So this helps us to distinguish the benefits between short and long lifetime components. So we could start to compare that on this graph here. And then we include this value, this performance reduction factor, when evaluating these two reuse recovery scenarios. So essentially, this graph is what we will use to then make design changes, which might then enable us to shift these curves up, the recycling, reuse curves up over time, the reclamation potential over time, and also to potentially understand which is the best recovery route to deploy. So this is something that we're scaling into a tool at the moment within the current project, a simple graphical user interface with the partners I mentioned before. And within this tool development, this is a very simple user interface where we can start to build up a product. So either we could extract that information automatically, as I showed before, or a user could come in and start to build up their product in real time and add the different associated components and elements and start to see a map of these components and how they connect to one another. And then we aim to showcase this in some sort of live dashboard, which the user can then see once they've completely populated their full system. And then based on this, start to make changes in the design, which may then influence these results. So just to conclude, really, just wanted to highlight to you the development of this assessment method to date of the reclamation potential as a method to understand the benefits of different design decisions on the ability to reuse and recycle products at end of life. And a key nuance in that is understanding the durability of elements. Our next stage is how to validate these assessment inputs, the probability of survival functions, and also the materials inventory, and continue to develop this web or app-based user interface in collaboration with practice. And we're very grateful to have Skouderbouw, the facade manufacturer, on board with this to date, but we're also open to looking at scaling it to other building elements and also other sectors. and understanding how this interacts with different economic business models as well for remanufacturing and could potentially be implemented into policy. So I'll leave you with that for today, and I'll very much welcome any questions and feedback that you may have.
Thank you very much, Rebecca, for a very interesting presentation. Very insightful. I like the concept of monstrous hybrid, very new to me. Well, we got some questions beforehand, but also there's one on the Q&A box. So probably I'm going to reframe it like, how do you see this method being scaled across industries, such as, for example, automotive? And what would be needed to adapt it beyond the built environment?
So I think that the concept itself, in terms of assessing these kind of multi-component systems, could be scaled to the likes of automotive or transport sectors, where we have typically this wide ranging mix of materials with these differing service lifetimes again. I think having the input on the deterioration of those components would be really key from those with expertise in those industries. So understanding those inputs would be essential for performing an accurate assessment. But the concept itself for using it to assess design changes, I think, could be readily applied to these other sectors.
Nice. Thank you. Remember to post your questions in the Q&A box. Another question we got before was, where do you envisage early adopters for this reclamation potential method?
So I think primarily in the first instance, it could be manufacturers actually with the direct influence on the manufacturing value chain. So looking at how they could incorporate different connection types that may promote reuse in future. So for example, maybe it's looking at using a dry fit connection, which may take a little more time to produce, but is more readily disassembled when it comes to end of life than a wet connection. And they have the expertise and experience to be able to do that on site to trial and perform those kind of activities practically on site. So manufacturers in the first instance, as a way to validate design changes. And then I think communicating that with designers is the next key step. And then potentially scaling to the likes of demolition contractors and clients and developers, for example, as well, who could start to potentially specify minimum values for reclamation potential and lifecycle environmental performance. So that could come into the client brief, I think, at some stage.
Okay, great. So we have several of our members being companies in the construction sector, and that's precisely why we're doing this webinar, because they can benefit a lot from. For example, we have Schuco, building door and window components company within our
Great.
members and joining us today. So if I'm that one of those early adopters, I want to know everything. So I want to know the limitations, for example, of that method.
So at the moment, I think one of the key ones will be ensuring that we fully understand performance deterioration. This data isn't necessarily always collected in real time for these components in different use cases. So, for example, aluminium components within close to the coast with different environments and saltwater environments. Can we get accurate data sets on their performance deterioration over time compared to aluminium components in an internal building environment? So inputting directly from manufacturers and demolition contractors to understand that information would increase the accuracy of these kind of methods. I would say that's one of the key limitations. And also opening up different use cases. At the moment, we are assuming that there is a demand for reuse of these elements in 50 years, but perhaps we want to reuse them in slightly different forms. So we are assessing for their technical reuse potential, but maybe there's a aesthetic obsolescence or otherwise that we haven't accounted for yet in these kind of methods. So understanding how we can incorporate those kind of uncertainties, I think, would be really key, particularly when we're looking at projecting future scenarios.
Makes sense. And we got a question also on demand for low carbon materials such as recycled aluminum, but I think this method that you presented is the opposite. So it's more about how can design for disassemble help or support that stable and sufficient supply of high quality post-consumer material. Yeah. So yeah, what is your vision between that growing demand for recycled material and your proposed method that supports design for disassembly?
Yeah. So I think, and also even through this method, you can start to see potentially in some instances over very long service lifetimes, maybe recycling is a better scenario to deploy when we have alternating forms to consider. So it may also encourage the high value recycling value chain as well. I think I see that at the moment, the collection of aluminium from buildings is already really quite mature for recycling. And so, yeah, I imagine it is likely if we continue to grow the demand for new aluminium products, and there's going to be a shortage for post-consumer recycled content aluminium. But then that's why I think it's also really important to look at ensuring that we lightweight, continue to investigate research areas that lightweight these kind of product designs up front to try and suppress to some extent that new demand, so that we can continue to grow, but at a reduced, materially heavy inputs, let's say. I think that would be best approach there.
Yeah, and you're touching a very interesting point because you're saying like the demolition and deconstruction of the buildings is kind of mature, but I think this is a European project, so I would say within this context is quite developed.
Mm-hmm.
But thinking about the global south and developing countries, so how this method can help them, where those deconstruction and demolition processes are sometimes even not considered.
Yeah, I think to some extent, actually, reuse though has more, could potentially have more of a chance logistically in these sorts of areas with sort of informal collection methods for reuse products. So maybe the recycling infrastructure isn't available for reprocessing, but being able to develop the necessary storage locations and, if necessary, reconditioning processes for direct reuse of these elements. Perhaps you're not able to achieve exactly the improvement in function as new, but reusing the elements as materials that they are without having to reprocess them. I think there could be many more opportunities for that in these kind of environments, I would say, local opportunities for reuse.
Excellent. And just one question, probably for Chris, who is as part of the attendee, but he normally question that, should we plan for really long life services or more like, I don't know, which is normally what we have on the West. But if we look at, for example, China, where they would like to um, build and demolish very quickly, so having shorter life cycles of the building. So what is your vision between the two and how this
Yeah.
tool helps us?
I think it's always really going to depend on the context and the element in question. Because, for example, that's where I see buildings as a really interesting case study as well for these kind of approaches. You always have this interaction between wanting to improve the operational performance of the building, but doing so in a material efficient manner. So, for example, if there is a new technology, if you've designed for this very long service lifetime with components that are not adaptable in any way, but we have new technologies that can improve the operational performance of the building. If there isn't a way to access the materials that need to be replaced and adapt them readily, then we will lose the potential benefits we could achieve in operational performance. So I think understanding the context is really key. What would be the benefits of adaptability, which we could start to plot alongside the likes of, in the context of buildings, operational performance, in other sectors, transport sectors, perhaps it's fuel efficiency or otherwise, mapping it to their potential trade-off and understanding which key elements need to be made adaptable to ensure we can incorporate new technologies where necessary. That's my approach there, I think.
Great. Just another question, and remember to post your questions in the Q&A box. So we are voluntary sustainability systems, and we certify companies. But how do you see this being linked to certification standards or even a policy recommendations, for example?
Yeah. So I think at the moment, I think it could be another metric, let's say. I think LCA is widely accepted at the moment, and also using Module D as this assessment for the circular economy, which I think is still very much a valuable approach to take, but just understanding what the limitations may be in terms of largely focusing on the mono material assemblies or the material alone. So I see this as another potentially a supporting metric for looking at multi-component products, and how this could come into certification or otherwise. Yeah, would be very much up for discussion, I think, to see how it could be picked up in a user-friendly way so that people can use it in a way that helps them, informs them to make design changes, but maybe they don't necessarily need to know the full extent of the method that's going on in the background. So how to communicate that, I think, will be key.
Thank you. You mentioned the development of the tool. So is there like any part of the tool that our members can access at the moment, or when is it going to be launched?
Yes, so not yet, but this project runs till January 2026. So we are running workshops with building practitioners, so stakeholders in the building value chain, some architects, some facade consultants, and also manufacturers around October, November this year. Some closed workshops in that sense, but we'd be open to inviting others as well if they would like to join that, because we're really going to use those sessions to get feedback on the usability of the first draft of the tool. And then beyond that, releasing it hopefully early next year, a very simple version of it. And yes, continuing to further iterate and develop it, and potentially looking at incorporating it as an add-on within existing software, digital design software as well.
Okay. One final question. So you showed the example of the system, the Windows, the system, the facade, sorry, the facade. Any other case studies of this being applied at the moment?
At the moment, no. It's largely been focused on curtain walling units as a great example of these differing service lifetime multi-component systems. And so we're very much open to looking into other building elements, structural flooring systems, other building envelope types as well, precast systems, and also internal units such as HVAC systems and mechanical and electrical services, I think would be interesting on the shorter service lifetime front. And then looking out into other industries, but then of course looking at support and engagement in terms of expertise with material performance within those sectors would be key.
Okay. Excellent. Excellent. Thank you, Rebecca, for sharing all your knowledge and your experience with the Reclamation Potential tool. Where can they contact you in case they want to follow up?
Yes, of course. So directly over email, I'd be glad to receive r.c.hartwell@tudelft.nl. And I can also share details of our research group as well after the session. So please, be happy to follow up and have a more detailed discussion.
And if people want to read a bit more about your work, where can they find you?
Yes. So we've published this work in an open access article in 2024, sorry, on reclamation potential in the built environment. So that is openly accessible, and that'd be one place to start. And yes, open to discussion or further involvement also in the stakeholder use of this tool that we're developing.
Okay, great. So thank you once again to all our participants. Thank you, Rebecca, for joining us today. Just look into our newsletters and members update for future events. And again, if you want to get in contact with Rebecca, you can do it through email. And if you have any further questions, you can also contact the ASI team. Thank you and have a good day.
Thank you very much.